I think there's interesting stuff today. Again, we are in chapter 10, which is a fuller expansion of the introduction we saw in chapter 2, section 4 on correlation and regression and scatter plots and things. We're using bivariate data, and we just finished 10.1, which was correlation. We learned a little bit more about R, Pearson's product moment correlation coefficient. I love saying that. It just sounds so good. You could put it on a little note card, right? Keep it in your pocket, and when you go somewhere, they'll ask you, hey, so yeah, if you go somewhere, nobody goes anywhere. You're standing 6 feet away from someone at a party, and they say, "How's statistics going?" And you say, "It's really cool. We're studying," right? And you look at your little card. Don't let them see you do that. "We're studying Pearson's product moment correlation coefficient." And it just sounds so impressive, doesn't it? What a way to put a bloom on the rose, to shine things up. So, we did that in 10.1, and we learned about it. And it's the usual thing with a two-headed arrow, and stuff in the far, far, far edges of that arrow are significant. And so we're looking for R's that are close to 1 or close to -1. R's close to 0, say, no, there's nothing going on here, move along, nothing to see. Okay, we're in 10.2, so I will share my screen and we'll look at the textbook. What was I going to say? Oh, and this is kind of review, right? Because we did see it in 2.4. So some of this will look very familiar to you, and we will, I hope, go a little bit deeper. If all we do is what we had in 2.4, then it will be boring for you. You'll be disappointed. But here we are, 10.2, regression. So it's a funny name, regression. And I'll explain what it means in a second, but what we're going to get is something called a regression line. And this will be, by definition, the best fitting line. So we're trying to get a line close-ish, if that's a word, kind of near the points in our scatter plot. We want the best fitting line. And does that mean the line that goes through the most dots? Well, maybe. Does that mean, yeah, and there's different ways to think about it, and I'll talk about a couple. I'll tell you how I used to do it when I was a little younger than you, and I'll tell you about how we do it, and we'll spend some considerable time on that. We will see the formula. We will never calculate the formula by hand. The kids in 153 have to calculate the formula by hand. I had a student yesterday. You'll chuckle, you'll chuckle. So 123, did I say 153? The kids in 123, Math in Modern Society, have one chapter which is statistics, and they learn about the normal distribution. They learn what a frequency distribution is. They learn some measures of central tendency. So they do the mean, the median, the mode, the range. They do these. And they learn to calculate a standard deviation, and they have to do it by hand in the table. And then they learn about R, and they have to do that by hand with a table. So they're adding up X's and Y's and products of X's and Y's and squares of X's and squares of Y's, and they're squaring the sums. And anyway, they go through this complicated formula. And a student came to me in my office hours, my online office hours, and said, "I don't know what I'm doing wrong." And she held up her page to her camera on her laptop and said, "It doesn't make sense because I multiply this out and I subtract in this part of the formula, I get the square root of a negative number." And I said, "Oh, well, that can't be right. Let me look at it." And I looked at it, and there was n equals 4. There were 4 data points, and I kind of checked in my mind her squares. I'm pretty good at squaring numbers, and so I saw that was right, and I estimated 4 times, and that looked right, and I could see that, yeah, I could see that it was going to come out wrong. And I thought, well, mental math, okay, let's try real math. And so I opened up a spreadsheet, I opened up Excel, and I keyed in all the values, and I actually calculated the stuff, and 4 times this and subtract that, and yeah, it comes out to a negative value, and you're supposed to take the square root. And I thought, well, this can't be right. The book isn't going to give them a problem that requires them to take the square root of a negative number. That wouldn't even work in the formula. It should be impossible. And so what I did was I opened up StatCrunch and I copied the data in, and I went to the regression tool and I said, do it. And it said R is 0.77. And I told the student, I said, I don't know how, I don't know why, but I could tell you the answer. It'll spoil your fun, but it's 0.77. And I hear her typing and she says, yep, that was right. I still don't know why. And I say, no, I don't know why either. Oh, wait a minute. And I had actually noticed before and then thought, oh no, I'm wrong. The problem was, you'll laugh, there weren't 4 pairs of data, there were 5 pairs of data. And we weren't supposed to multiply by 4, we were supposed to multiply by 5. And so here was this student by hand doing this ornery, rigorous, tedious, complicated calculation with all kinds of squares and square roots and multiplications and subtractions and fractions and crazy, crazy stuff. And the place that she made the mistake is that she couldn't count up to 5. And I laugh because, well, I couldn't either. I tried it twice and I got 4 both times. So anyway, there are complicated formulas for this in 10.1. That's the R. There will be a complicated formula for the regression line, and the student had to do that too, and she was much more successful once she realized there were 5 pairs of bivariate data instead of 4. This regression line, by the way, starts with the letter R, and that's why Pearson's product moment correlation coefficient, none of which has R's in it, is called R. So R is really a short for regression. And why is it called regression? Well, here's the idea. Let me see if there's a plot here. I really want to show you a plot. Let me find one. I'm going to find a plot. It's not a very good one, but it's on page 492. I say it's not very good because it's useless, and we already know that even though there is a correlation, this is garbage as far as meaning something. So this is the chocolate and the Nobel Prize winners. We've talked about this several times. So here's the idea. The idea is that as X, whatever it is, imagine this is just a generic scatter plot. As X increases, Y increases. Okay, makes sense. And so here's X, it's going up, it's going up, it's going up, and Y is going up, and X is going up. Oh wait, what happened to Y? Y kind of, oh, shouldn't it be higher? Yeah, it should. These people aren't trying hard enough with the measurements are. And here we're going up, we're going up, we're going, oops, there's a little slip, and we're going up, and oh no, we're falling back down. We're going up, we're going, oh no, we're falling down. And Galton, Francis Galton, noticed these fall downs, and he considered this a regression, because what he was hoping was that, remember, he was studying animals, he was studying people, and he had this idea of genius, and he had this idea of the progress of the human race, and people should be getting healthier, they should be getting taller, they should be getting smarter, they should be getting more industrious, they should be getting more honest. He considered honesty something that you could graph on a chart, you could measure it somehow. And he thought that the human race should be improving, and every once in a while it doesn't, and he considered those regressions. And so he called this a regression line. You can think of regression, another example I give the kids is, think of the average record album. And I don't know if they have record albums anymore now. I mean, the whole world has changed, thanks to Steve Jobs, who changed the way music is sold. With iTunes, right? It used to be, when I was your age, if you wanted to buy a song, well, if it was a single, you could buy the single, and it was on a 45 RPM small record with a big hole, and you had to have a special attachment for your record player, and you could buy a single, and it would have an A side and a B side, and the A side was usually something you wanted, and the B side maybe not. That was the only way you could buy one song. And if a song wasn't released as a single specifically by the band and the recording company, then what you had to do was buy the LP, which was the whole album, and it had maybe a dozen songs on it. And if you only wanted one of them, well, you kind of wasted your money because you also bought 11 other songs. And Steve Jobs came along and said, hey, let's do this in iTunes, and we'll let people buy one song at a time for 99 cents. And if people don't want the other 11, they don't have to have them. They can just buy. And it totally changed the world. And you're living in it. You're thinking, oh, yeah, that was a thing before where you had to buy. Oh, yeah. But going back in time for my example, if you think of the typical album, the typical music album just isn't very good. It's kind of average. It's kind of pedestrian. The songs are nothing to write home about. They're just songs, and nobody plays them on the radio. Nobody plays them at home either. That's the typical average album. And then once in a while you get an album like, and here I'm showing my age, but Rubber Soul or Sgt. Pepper, right? Or, you know, these big albums. And you can think in your own time of some hit like that, some amazing album, or even an individual song. The average song isn't very good, and that's why Steve Jobs changed everything. Most people don't want the other 11 songs on the album. They want the one song that's the hit. If you think of your typical band, so here comes this boy band. Make up your own name. In the past, I've used silly names for the boy band, but anyway, there's a boy band, and they come out with a song, and of course it's garbage because most songs are. And this isn't, you know, I'm not being a curmudgeon, oh, the old guy doesn't like boy bands. No, it's just most songs aren't, and that's not a judgment, that's not a criticism, it's just I'm a statistician and I know what average stuff is like. It's kind of average. But every once in a while, some boy band comes along, and their first album, oh my gosh, listen to this, the beat and the backbeat and the vocals and the harmony and the lyrics, and the little girls raise their hands in the air and scream as loud as they can, and everyone's thrilled by this. And then what happens? Then they come out with a second album. And their second album is kind of average, because most albums are average. And someone could look at that first album and say, oh man, it was so great. And this second album is kind of stinkeroo. It's not as good. They've regressed. And so this is this idea of regression. And regression isn't something that, oh, the band suddenly got worse. No, most bands are average because they're most bands. They're on the average. And the fact that their second album was average is just what everyone should expect. The only reason we're disappointed, the only reason we thought of this idea of regression was their first album was unusually, if you want, you could say statistical significance, their first album was unusually good. And so we say the second album regressed. No, the second album was just what they would have put out all the time, except this first album was unusually good. And so this stuff happens. Here's this idea of regression. And they do mention Francis Galton, 1822 to 1911, studied the phenomenon of heredity. When tall couples have children, the children are tall. And when short couples have children, the children are short. Except the really tall parents do have taller children, but not as tall as they are. And the really short parents, they do have shorter children, but not as short as the parents are. And so Galton considered this as a sort of regression. The heights of the children tend to regress. They become more average. Like the boy band, their second album is more average because that's what happens. And so since this was in the late 1800s, this is like 1880s, 1890s, he's doing this. And everyone calls it regression. So here we go. Hey, this is the stuff we learned in 2-4. Yes, cool, isn't that nice? So that's why I can tell long stories. We won't fall behind because there's not a lot new here. We have this idea of the regression line. It's also called the line of best fit, or the least squares line. We have no idea why it's called those things in italics. We will explain it. in a short time. But for now, we call it the regression line, and that always works. It's the line that best, and he puts this in scare quotes, in quotation marks, because what do you mean best? You mean it hits most dots? You mean it's closer to, what do you mean by that? And we'll see what it means in a minute. But right now, we don't know. But the regression line is defined as the line that best fits the scatter plot, and the regression line has a regression equation. And if you think back to your junior high and high school math days, you had lines, you had equations for straight lines, and they looked like y equals mx plus b. And if we were in class, maybe in your notes you'll want to write y equals mx plus b. That's the equation for a line, and that should sound kind of familiar to you. It's one of those things that people remember. I'm always surprised at what people remember. I teach the algebra class, and they come in, and we kind of assume that they don't know a lot. I mean, they should know basic arithmetic, but we start at the bottom and move up. And when we get to the section on Cartesian coordinates and graphing, about 2/3 of the class remembers y equals mx plus b, and I'm always kind of surprised that that sticks in their mind. Somehow that's meaningful and memorable. So here's y equals mx plus b. Yeah, except we're not math people right now. We're stats people, and stats people, they ruin everything. The early statisticians, I've mentioned this before, they weren't really mathematicians. They were physicists, or they were biologists, or they were philosophers, or they were whatever they were, and they used notation which kind of annoys math people. And so, for example, we don't say y equals mx plus b, we say y hat. And why is it a y hat? Well, because it's not the real line. This is a prediction line from the data that we have. And so y hat here, this is the response variable, and it's not the actual value of anything, it's just a prediction. If you give me an x, look, there's an x, and I can plug it into this equation, and I can get a value which I will plot on the y-axis, but I'm not going to call it y because it's not really the value that goes with that x, right? If you flip forward to the chocolate consumption, you look at the line and you see where the, well, let's do it. I don't care. We got a minute. It'll make more sense for you. Here's the x-axis, chocolate consumption. It goes from 0 to 14. And here's the y-axis. And this black line, I guess the dots are red and the line is black. Hard for me to tell, but this black line is the regression line, and it's y hat equals da 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 da. And what I'm saying is, if you put in an actual value for x, so here's an actual value for x, it's 7.29, you know, and I'm making up the decimals because obviously I can't tell that scale, but there is some actual value of x for this particular dot, this particular data set, data pair in the scatter plot. So I know what x is. It's right there. If the points were labeled, you would know. And then you plug that into the regression line equation, the regression equation, and you get a value out. Well, you get this value. You get the value that's on the line. Well, that's not the correct value for y. The correct value of y is where it is. You know, it's 5, it's 6 something. It's right here. And the value we got out from the equation was 12 something. Well, that's way off, you know, and you can see this one, it's way off. You plug in this value of x, which is 8-ish, and what do you get back? You get back 16 something. And what you should have gotten, the real y value, is 24, right? And so this is why we put in the y hat, because we're not actually getting out the y, we're getting out a prediction. And if our regression line is good, it's pretty close, it's the best we can predict, but we're not going to get exactly it. So continuing, y equals mx plus b. The y isn't a y, it's a y hat. And for reasons that aren't clear now, but will be clear in 10.4, we don't say mx plus b, we say b plus mx. And that's kind of Why did they have to change the order? I finally understood something in math, and then they switch it around. Yeah, that's a reasonable gripe. Um, when we get a couple sections in, you'll say, oh, there was a good reason for it, and there is a good reason for it. The other thing is, instead of calling it M, they call everything B. Well, I'll tell you the reason why. The reason is later on we're going to throw in more explanatory variables, and so there won't just be an X. There'll be an X. There'll be lots of X's, different values of X's. And what does that mean? Well, I'm not just measuring chocolate, I'm also measuring rutabaga consumption, right? And so, oh, now you have, here's a country, how much chocolate do they eat, how many rutabagas do they eat, how many Nobel Prize winners do they have? And so it becomes a more complicated, there are other factors that are involved. And the point was that if you want to put more factors, because once you put in rutabagas, then you think, oh, well, let's put in orange juice. Okay, so now we've got 3 different factors, and you keep getting more and more factors. Well, then you can still extend it out, because you have a B0, you have a B1, you have a B2, you have a B3, you have a B4. And this is why they switched the order, was so it's easy to add stuff on at the end if you needed to. So anyway, I don't know if you needed to know any of that, but there it is for you. X is called the explanatory variable, and I've mentioned to you that that's a fabulous mnemonic if you're trying to remember. The explanatory variable, this is the thing you think is the cause. I think that chocolate consumption causes the number of Nobel Prizes a country gets. And we know that's nonsense, but that's what we're thinking. I'm thinking that someone's height determines their weight. It affects their weight. Typically, tall people are heavier than short people. And yeah, there's exceptions, but I'm thinking that. I'm thinking that the amount of study time affects the person's grade. It's not that the grade affects the study time. It's not that, oh, this person is really, really heavy. Well, they must be tall. It's not that, oh, this country has a lot of Nobel Prize winners. That must make people eat chocolate more. No, that doesn't make sense. So we're thinking that the X is the explanatory, and if you think you know, so you have these XY pairs, you measure the weight and the height, you measure the study habits and the grade, you measured whatever it is, 2 things. If you think you know which one causes the other, then you should put that one, the causal variable, on the x-axis. If you have no idea, well, it doesn't matter. No, doesn't matter. But if you think you do know, then put x as the explanatory. It's the predictor. And the y hat is the response. That's the effect. So cause and effect. He mentions independent variable and dependent variable. He does this because he thinks you were that student. I'm thinking of all of you. I bet a couple of you might even remember dependent and independent from high school math. I think a couple of you did take a fair amount of high school math, and maybe you're familiar with those terms. Well, they're great in high school math, but they have nothing to do with statistics. They're never used by statisticians. You will never be asked to call them that. You will never be asked to identify them as such. You don't have to be able to recognize these terms. Wipe them from your memory. We don't call them that. And why do we not call them that? Because of chapter 9, we had 9.2 and 9.3. We had independent samples and dependent samples. It means something totally different. And so don't ever be caught calling X the independent variable. In high school math, in graphing, yeah, you can call it that. In physics, you can call it that. But don't call it that here. Don't call Y the dependent variable. So explanatory variable, response variable, that's your X and your Y hat. And you're thinking, gosh, Gary, we knew this in 2.4. This is review. Move on. Okay. Here I go. The green stuff. How do you find the equation of a regression line? Well, remember that this regression line is a prediction. It's based upon the sample data that you have. It is not the correct line for your population. I've only measured the heights and weights of a few penguins, not every penguin in the world. And what that means is that these B values, and that's what you're getting out, the B0 and the B1, are sample statistics. They relate to the penguins I actually measured. In the real world, in the heavenly realm where they know this stuff, in the population, and we'll never figure these out because I'm not going to go measure every single penguin, but there are betas, and here again, this is something we've seen before. Use Latin letters, regular alphabet letters for sample statistics, and use Greek alphabet letters for population parameters. And so this beta, it's the second letter of the Greek alphabet, alpha, beta. That's where we get the word alphabet, alpha, beta. So this is a beta. This is a beta, and corresponding to B0, the sample statistic, there is a beta 0 population parameter, which we are trying to predict. And corresponding to the B1 sample statistic, there's a beta 1 population parameter. Corresponding to the Y hat regression line, there's a Y regression line. And see now why I made such a big fuss about this Y hat and this Y. What is this B sub 0? It's the y-intercept. So if you think of y equals mx plus b, this is the b. This is the y-intercept that you learned about in high school. We will almost always ignore that as being meaningless. And why do we almost always ignore that as being meaningless? Because think of how you get the y-intercept. The y-intercept occurs when x is 0. So you look at this regression line equation. If my x value is 0 and I plug it in, well, then what does y hat equals? It equals b sub 0. That's the y-intercept. Well, what does that mean? Well, I measured a penguin, and I think that his height predicts his weight. And how tall was this penguin, Gary? Well, this penguin was 0 centimeters tall. Oh, then what did he weigh? Well, this is a stupid question, right? And so almost always in the real world, remember, it's a thinking class, not a math class. There, I said it. Remember that in the real world, the y-intercept probably doesn't mean anything because it comes about when your x value is 0. And when is your x value going to be 0, right? No, I could think of one. We were talking about study habits. The number of minutes spent per week studying, that's your explanatory variable, x, and y is the grade you get at the end. And it would be possible for a student never to study a bit, but I can tell you what their grade's gonna be. So yeah, once in a while, maybe it means something, but almost never. So typically we will ignore this. And if you think back to 10.1, we were looking at some charts of things, and we had an intercept and we had a slope. Well, this B1 is the slope, and we had to look at p-values to see whether we had found something meaningful. And I said, look at the p-value on the slope, ignore the p-value on the intercept. And that's why, because the intercept doesn't really mean anything. It's an artifact of the data that you have. So there's the meaning of all this stuff. Requirements. Oh my gosh, there's a lot of requirements. Yeah, they're exactly the same requirements we had in 10.1. So if you remember that, the samples have to be a random sample. Yeah, and when you look at it, that's the visual examination. When you look at it, it better be a straight line. If it doesn't look like a straight line, don't waste your time getting a formula for a straight line, because that would be, who would do that? Outliers. Outliers mess stuff up royal. One single outlier can totally change the whole thing. So think about outliers really, really hard. Blah, 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 blah. This is the same stuff as in 10.1. I'm not going to reread it to you. It's in your notes. So how do you calculate the slope and the y-intercept? Well, to get the slope, what you do is you take R, Pearson's product moment correlation coefficient, and you multiply it times, this is the sample standard deviation of the y parts of your bivariate data. This S sub x is the standard deviation of the x part of your bivariate data. So each of them has an x and a y. You take all the y's and you find the standard deviation. You take all the x's, you find the standard deviation. You turn it into this little fraction, you multiply it times r, and you know the slope. And you already know what I'm about to say. We will never actually do this because StatCrunch does it for us. We click and it's done. But there you go. That's how you do it. And you think to yourself, whoa, you have to find the standard deviation of this? Yeah, you do. Yeah, and the 123 kids have to do it. Oh, well, how do you find the y-intercept? Well, you take the average. This is the mean, y bar, the average of all the y's, and you subtract the average of all the x's, x bar, times that slope you just found. And so, you know, it's not hard to find an average. This is, if someone said, which one of these do you want to do if you're doing it by hand, you should always pick the y-intercept because it's easier to find an average, a mean, two means, and then when you get done with the slope, tell me the value and then plug it into this equation and you'll know the y-intercept. This is a nice explanation. If you're actually doing them by hand, you probably want to use a table, and you'll have a table of x's, a column of x's, a column of y's, a column of x times y, a column of x squared, a column of, well, if you're finding r, you need a column of r squared. But here r is built in. If you don't want to do it this way, you could do it by hand this way using a table. And you can find the b sub 0 pretty much with the same table, right? Most of these values you already have. I already added up all the y's. Oh, yeah, cool. There it is. Multiply it times the sum of all the x squareds. Well, I didn't have to do that before, but it's one extra multiplication. These aren't super hard if you set things up in a table. You round it. Yep, there's a rule. We don't care what the rule is because the blue stuff will tell us. If we need to know, we will look it up. So how do you do this? Well, you use technology. And so you key in or you copy in a bunch of XY bivariate data, and StatCrunch comes out and it says the dependent variable, you have to tell it which is which. The dependent variable is the Nobel Prize winner numbers, and the independent variable, and yeah, I don't like these words any more than you do. I just told you don't ever use these words, and then they use them in StatCrunch. Well, yeah, right. Look at everybody else. Look at everybody else. Look at everybody else. I told you statisticians don't use those words. Yeah, StatCrunch. Read between the lines. Real statisticians don't use these words. But here you go. The dependent variable, that's the x. Sorry, the independent variable is the x chocolate, and the dependent variable, that's the y, is the Nobel. And so y hat, the result will be, and here is your b sub 0. Remember, that's your y-intercept, which we don't care about because it's kind of meaningless. Plus slope, this is your b sub 1, times the independent variable, which is your x. And if you had a TI-83 and you didn't mind keying in all the values, your TI-83 will actually do this. And it even gives you a t value for the thing. It figures out your degrees of freedom. It tells you your A is your b sub 0, and a b, which is your b sub 1, the slope. And anyway, and it does that. Others do it in different ways. If you ever get out in the real world and you have to do it, you look in the index and you say, how do I get a regression line? It'll tell you a page number and you'll go and do it. So you can use manual calculations. I told you you should use a table if you want to do that. And they don't even show you it. They just do it. Okay, yeah, you can do it. Believe us. Okay, so now we finally get to something with meat on its bones. It's a thinking class, not a math class. You have this value of r, and you have values for b sub 0 and b sub 1, which gives you a regression line equation. Now what? Why do you want the regression equation? Because someone's going to come along with an x value, My X value is exactly 8. I've just found a country, and we haven't measured them before. I've just found a country that eats exactly 8.0 kilograms of chocolate annually per resident of the country. How many Nobel Prizes winners should we expect? And we've never had someone with 8. And so what do? Well, hey, it's probably about this. It's probably about 15-ish, 16-ish. And you'd plug it into the equation and you could do it. So what we're doing is we're making predictions for values that we haven't measured. That's our goal. This is inferential statistics. We're predicting the value. So there are some situations that arise. It's possible that everything you've done is crap, meaning, no, don't use this. Why would it not be good? One reason it might not be good is, well, I got this curvy line. Well, if you get a curvy line, don't be using a regression line model to predict values, because the regression line model is a straight line, and you looked at your graph, you're smart enough to do that, and so if it's not a straight line, don't be using that model. Another reason is, well, the dots are kind of all over the place, and when I calculated R, it was 0.061. Well, that's a really, really small R. That means you have no statistical significance. There is no mathematical correlation detected. And so if you have that R, you can plug in the values and you can get a y hat equals b sub 0 plus b1 x, and you could plug in your x and it's garbage. So if you have a bad model, your R is too small, or your line is not actually straight, your predicted line, when you look at the dots in the scatter plot, don't do it. If you have a bad model, so if you can't predict well, then what should you expect to get? The predicted value of a variable? It's the mean of the sample. So I measured a bunch of penguins and their values were all over the place. Well, hey, I just found another penguin and he's 22 centimeters tall. What do you think his weight is? Or weight rather, he's 22 kilograms. Whoa, that's a whopping big penguin. Let me start this example over. We've measured a bunch of penguins. We measured their weights, we measured their heights. I think that the height explains the weight. There we go. The height explains the weight. I'm thinking that taller penguins weigh more than shorter penguins. And so I have the height and I have the weight, and this is my theory, and I plot the things, and I get a very, very low R value, and it doesn't seem to be able to predict things. Right, then someone walks in and says, hey, did you get all that equation stuff? And I say, well, kind of, because I didn't. Once I see the R is no good, I'm not going to waste my time finding the equation. MATLAB might ask you to, or they might give you an equation because it's very easy. It's click, click, and you don't even have to click anything extra. You have the equation. You can't calculate R in StatCrunch without getting the equation. So I have this R and I have this equation, but I looked at my scatter plot and the dots are kind of everywhere. And I looked at the R and it was very, very low. And I looked at the p-value and it was a whopping big p-value. And I'm thinking, this means there's no correlation. This means my formula is no good. And someone walks in and says, hey, we just spotted a penguin with our binoculars and you're thinking that the height explains the weight. And I say, well, yeah, that's what I started with. That's why I came to Antarctica. Well, if the height explains the weight, can you predict the weight of this penguin spotted through our binoculars? This penguin was 28 centimeters tall. And the mistake would be for me to take that 28 and put it into the equation, because that's not the best prediction. The best prediction is, well, I caught 20 penguins and I found the mean weight, the mean height. This penguin he spotted, if I want to predict its value, I'm going with the mean. And this goes way back to chapter 7, right? Estimating a population mean. You're trying to predict a value. It's the best point estimate. The best point estimate is the sample mean. And you say, how tall do you think that penguin is? I don't have any other data to work with. Yeah, but I told you he's really heavy. And so don't you think he's, or sorry, I'm getting it backwards every time. I told you this penguin is really tall. Don't you think that makes him heavy? And I say, well, I thought that, but then I plotted a bunch of heights and weights, and it didn't look like they did really relate. It made sense in my mind, but in reality, I didn't see it. The math didn't see it. And so in that case, you will always use the sample mean. And you will have situations like this in your exercises where they will give you a bunch of stuff. They'll give you R and they'll give you the Y hat formula for the regression line. They'll give you X bar, the average X, the Y bar, the average Y. I should be saying means instead of average, but you know what I'm talking about. X bar, Y bar, and then they give you some new X and they say, what's Y hat? And you have to be careful because if it's a bad model, you just copy in whatever Y bar is. You use the sample mean. Okay, well, what if it is a good model? If it is a good model, in other words, yeah, it looks like the dots are kind of straight and R is pretty big, close to 1, or pretty big, close to -1, and my p-value is small, I think there is a correlation. Well then, yeah, take your 8 and plug, you'll get the thing. Okay, well that was easy enough. There's bad models and there's good models, and don't use bad models, use good models, and great. Now wait, there's some complications. And one complication, well, let me show it to you. I already talked about correlation. It's a bad model if your R is no good. If your R is really small, meaning your p-value is really big, then the dots are all over everywhere, and you'll spot that. So here's the idea. I've got this fancy formula, and I think I can use it. We know it's meaningless, but mathematically I can use it. There is a correlation. Correlation doesn't imply causation, and we know chocolate isn't actually related to the Nobel rate. There's a lurking variable, but for the purposes of this example, I've done all this work with all these different countries, and then someone comes in and says, hey, I found one more country that we've never measured. And I actually don't know how many Nobel Prize winners there are. I only know how much chocolate they eat. But you can predict, can't you? And I say, well, maybe. And you're thinking, well, of course you can predict. Why do I say maybe? Well, here's the situation. The scenario continues. How much chocolate do they eat? They eat 20 kilograms per year. Each person eats 44 pounds of chocolate. That's almost 4 pounds a month. That's a pound a week. Oh boy, wouldn't that be great to eat a pound a week of chocolate? As long as it's dark chocolate, I think I could go along with that. But anyway, the guy says they eat 20 kilograms. And so over here where my cursor is wiggling, that's 20. I don't have any data like that. My data goes up, I don't even have 13. If you want me to predict stuff out here, honestly, I have no idea what the dots do. It looks like they go straight, but they might go straight, whoop, and then they go up. It might turn into kind of an exponential thing. Or they might go straight, and then they kind of flatten out. Well, if I just go straight, if I use my linear equation with a input, an explanatory variable value of 20, which is way outside of my range, then the technical term is I'm extrapolating. I'm going outside. Extra means outside. Extraordinary means out of the ordinary. I am out of my data range. And if I'm out of my data range, I don't really have any confidence that this line continues in the same trajectory. There's lots of things it could do. And so if someone says, okay, what do you get for Y hat for 20? I'm going to go to Y bar again. I'm going to go to the average because I have no idea. It would be improper statistically. It would be foolish to try to plug in a value that is beyond the scope. So watch out for that. There you go. And this is all summarized in a cute little chart. Does it look like the points are close to the line? And does it look like they're straight? I guess if they fit, then yeah, they look straight. Is R big enough positive or negative that we think there's a correlation, is the prediction within the scope or not much beyond the scope. Well, yes for all of those, then you plug it in. And no, I don't care what X is. You don't have to pay attention. You don't have to put it in your calculator. You just tell them the Y bar, the mean of the Y values. And they give you an example of that, but I think it's so easy, I kind of don't want to do it. Okay, some extra stuff. Marginal change, because this is a topic in calculus. It's also a topic in economics. So if any of you were a business major, you might have heard this idea. The marginal change in a variable is the amount it changes when the other variable changes by exactly 1 unit. And so let's go back 2 pages. Here's our chocolate stuff. And here's 6, and there's where the line is. It's 11. And here's 7, and here's where the line is. It's 14, 13 and a half. And so going from 11 to 13 and a half, because what did I do? I went from 6 to 7. I went 1 unit of chocolate. Well, how many units of Nobel Prize winners is that? Well, it's about 3.5. You say, well, how about if you go from 4, which is 6, to 7, 4 to 5. I had that problem last night trying to count from 4 to 5. 4, what did I say, is 7-ish, and 5 is about 10, and yeah, it's about 3. And if you go from 10, which is 22, to 11, which is 25, oh, it's about 3. Well, it's always going to be 3, right? Because y equals mx plus b. Ignore the b, you're changing the x1 value. Well, you're multiplying it times n. You're multiplying it by the coefficient b1. And so that's the slope. And in fact, the marginal change, if you change x exactly 1 unit, then it's multiplied by the slope. And so b1 is the marginal change. That's how much the y will change. So here's the example. I was saying it was about 2.5, and oh yeah, it's actually 2.49. And you could look at that and plug in a value, plug in a 9, and then plug in a 10 and see what the difference is. It will be exactly 2.49. So that's the idea of marginal change. If you're in one of my calculus classes, I would spend some time telling you why it was called marginal, but I don't know if you need to know. Outliers and influential points. We already mentioned in the green stuff, in the requirements, that outliers can affect the regression line equation in a drastic way. I'd like to say in a significant way, but significant means something in statistics. So just say a drastic way. It can really, really change it. What is an outlier? An outlier is any point that's far away from the other data points. Well, what do you mean far away? And that's where it becomes just a little bit tricky, because you can have points that are far away that actually don't influence the line. Then you have some other outliers that do influence the line. So earlier I said an outlier can affect the line in a drastic way. It doesn't have to. And why would that be? Let's look at this next page. I think they have an example here. So, and they don't have a good example. I'm going to have to use the whiteboard and show it to you in a second. Here are our original chocolate values, and they've been plotted for us, and we know it's a negative 3 point something plus 2.49x, and that's the equation for this line. And then someone comes in and says, hey, I do have one more data point, and the data point, is it an outlier? Yeah, it's 50. This only goes up to 14. And so on this scale right here, 2, 4, 6, 8, 10, 12, 50 is, I mean, my cursor won't even, it's off your screen. That's where 50 is on this original graph. And so this scale is much, much reduced. If you go from 0 to 14, that's from here to here. I mean, that's just a little piece of this scatter plot. And we have this new data. It's so far away we had to extend our scale. By definition, a point that is far away is an outlier. Well, also notice what happened to our slope. This guy's really flat all of a sudden. Okay. We've got lots of time. Let me jump over to the whiteboard, and I'll show you the two situations, and this will make more sense to you. So, grabbing my pad, grabbing my stylus, we're making a little scatter plot, and the scatter plots will be blue, there are some data. Here is a very similar scatter plot. In fact, it's exactly the same scatter plot, and I don't know if I can, I mean, obviously it isn't because I'm not that precise, but here's another scatter plot. It's exactly the same. I've plotted the same thing twice. And then here comes one extra point, and I'm going to make the extra point black. Here's the extra point. Is this an outlier? Yes. How can you tell? Because it's not close to the other points. Okay, so there's an outlier, example 1. Over here, in example 2, I am also going to add an outlier. Here's the outlier. How can you tell? Because it's far away from the other points. That's what an outlier is. So now let me switch. I'm going to use red for my regression line. And I'm thinking my regression line should go about like this. Wouldn't you say that? And then, well, wait, there's one more point. Okay. What did this outlier do to this regression line? What did this outlier do to this regression line? It didn't do anything to it. It's an outlier because it's far away from all of these blue points, but it didn't affect the regression line at all. In fact, the regression line goes right through it. Over here, here are a bunch of points. Watch this little hand. Where should the regression line be? It should be right through here. Yeah, but there's an outlier here. Okay, well, let me fix it for you then. Here's where the regression line would be, including that outlier. What has happened? So here is an outlier. Here is also an outlier. The difference is that this one, only this one is an influential point. And why do we call it an influential point? Because it influenced the line. The line here is totally different from our original line. It has a different y-intercept and it has a different slope. And why did it change? Because this outlier influenced it. Not every outlier is an influential point. And this is just one more reason why you might graph your data. Because if you graph your data, my screen's doing something funny. I'll ignore it and keep talking to you. If you graph your data, you can look at an outlier and you can tell whether it will be influential or not. Does it kind of seem in line with the rest of the data? Yes, then it's probably not an influencer. It's probably not an influential point, and you don't have to worry about it so much. This point here, this outlier, I'm going to worry about a lot because I'm thinking, wait a minute, Who measured this penguin? Was it Fred? Was he drinking again? Oh, Fred. If this particular data element is wrong, if it was recorded in error and that happens, I don't want to include it in my formula. But if there actually was a penguin that was this tall, this heavy, and this short, well, that's kind of interesting. And I always tell the kids, that's you, it's a thinking class, not a math class. And with outliers, there's two things that outliers can be. One is outliers can be weird stuff that doesn't make sense. It might even be weird stuff that is an error and shouldn't be included at all. But also, and this depends on your context, you're the researcher. An outlier might be where all the meat is. This might be, we figured out something. This is our conceptual breakthrough. Back to the lab, we're going to start making these. We're going to tweak some stuff. We have 3 new experiments we're going to try and figure out why this outlier. Sometimes an outlier is the thing you're looking for. And you don't know ahead of time. That's part of the thrill. If you always knew how it was going to come out, this statistics would be boring. And I'm hoping after so many weeks with me, you're thinking, well, yeah, it is kind of, but there were parts that, yeah, okay. So this is one of those parts where, whoa, maybe. And so you do have to be very, very careful with outliers. Does that make sense to folks?
Yes, yeah.
Yeah.
Okay. Let me go back to the, and this is something else that I like to draw, and I wish I could, but I'm going to try it out of the book. Usually I draw it for the kids. Decisions. I'm not going to. The book example isn't horrible. The reason I like to draw it on the board is if I draw stuff on the board, a lot of kids write it down. And taking notes is really, really valuable. And if I tell kids, this is on page 496, then they stare at it, but they don't write it. And stuff you stare at goes whoosh, into your brain and whoosh, out of your brain. And that's not what you want to happen. And if you write it down, it goes whoosh, into your brain, and it takes a little bit of time before it's gone. And so you'll learn it better. So with the caveat that you probably should copy this into your notes, let me show you this next little section. So we have a new formula for something else. There's a new vocabulary word. It's a very, very, whoa, I was on the page. Never mind. It's a very, very easy thing to calculate. It's right here. This is called a residual. So you have a bunch of XY values, and you take one of the XY values. It has an observed Y. What's the observed Y? That's the Y value. That's the Y that you actually measured the penguin and you got. And then you have the predicted Y. And what is this? This is the Y hat. This is what the formula tells you what the line predicts. So you have this regression equation and you find out what Y hat is, and then you take the value you actually measured and you subtract them and find the difference. And that's called the residual. So easy enough. Let's look at an example now. So here's a point right here. This point is 9, 2. And this point, well, here it is. It's 8, 4. I was close. This point is 8, 4. And this point is 12, 24. And this point over here is 28. And this point over here is 24, 32. So these are these different points. And we have plugged these in to the formula. No, we haven't. We used StatCrunch. We're not going to do calculations in this class if we can avoid it because we're lazy. We've used StatCrunch, and the technology has reported to us that the regression line equation is Y hat equals 1 plus X. Okay, nice enough. X is 8. So here's my 8 up here, 8. I can't color in the 8. Well, that's what you get. Imagine I've colored in the 8 for emphasis. And what was the actual value? The observed value was 4. What does this regression formula predict? If you plug in the 8 for your x, you get 1 plus 8, you get 9. And here you can actually see there's the point, this line, 8, 9. And it's not colored in. If I were doing it in class, I would color it in and I would label it. I would say y, I would say x, y, and this is x, x, y hat, and this is x, y. And so you say, well, wait, we just predicted 9, and it actually was 4. Yep. So 4 minus 9 is -5. That's the residual. And we'll do one more of these, and you can do the rest yourself. This one, the x is 12, so x is 12, and the point is right here. The y was actually 24. If we use the prediction of the regression equation, we say 1 plus the x value of 12. 1 plus 12 is 13, and here's the point 12, 13. And you say, how far is it from 24 to 13? 24 minus 13 is 11. So there's the residual. There's a residual, there's a residual, there's a residual, there's a residual. You can use these residuals to tell if your line is close. And the way you do that is you add up the residuals. And spoiler alert, this isn't going to work for the same reason that adding up the deviations. This is kind of a deviation, right? A deviation, remember, was the distance from the mean. These residuals are distances from the predicted value, the y hat. And so if you add up -11 plus 7 is -4, that's a positive 11. 11 plus 7 is 18, minus 5 is -13, minus 5 is 13, minus 13 is 0. Oh, shoot. And yes, this will always happen. You'll get zeros. And the same if you add up all your deviations when you're calculating a standard deviation in a table, you'll get 0. And in order to avoid the fact that the negatives are canceling out the positives, what we did when we calculated standard deviation way back in chapter 3 was we squared all of the deviations. And that's what we're going to do here, is we're going to take those 4 residuals and we are going to square them. And so we have -5, square it, you get 25, square it, you get 121, square it, you get 49, square it, you get 169. Add those together, that is the sum of the squares of the residuals. Is this a good line? So before we said what we're looking for is the line of best fit. How do you decide that a line is the best fit? If the sum of the squares of the residuals is the least possible value. And we call a line that satisfies that a line that satisfies the least squares property. So we added these up, 25 plus 121 plus 169 plus 49, we got 364, and the claim is made, and you could check it, maybe in Desmos or some graphing tool. Anyway, try any other line and calculate the residuals and square the residuals and take the sum of those squares, and you will get something bigger than 364, because this is the best line. It is the best fit. Why? Because it satisfies the least squares property. There's no other line which will have the sum of the squares of the residuals be a smaller value. How do we know that this regression line really is the best regression line you can get? And what we did was we took the predicted value. This is the hat value for 12. The y hat value predicted for 12 is right here. It's 13, and the true value, if you look up in this chart up here for 12, the x value of 12 had a y value of 24, and so being at 13, well, we're 11 off. That's quite a ways off. If you look at 8 here, the prediction is 9, and the actual value of the data that we were supplied with was 4. And so from 9 to 4, we have to go down 5. There's a negative residual there. And we looked at this. I want to show you this again just so that you get the feel for what is going on, because as soon as we get into 10.3, we will see a chart that looks very, very much like this, and we'll give slightly different names to these things because we'll be thinking of them conceptually as a slightly different thing. But I want to emphasize that. And what did we do with the least squares property? What we did was we took each of those residuals from the actual data and their differences from the prediction line, and we squared them. If you add up these values I pointed out, they just cancel. They turn into 0. And that's not very useful for us. But if we square them, then we'll get some positive value, or at least non-negative value. And we want the smallest one, and that's called the least squares property, because we've squared all the residuals and we want the least value. And that's the definition of the best fitting line. Okay, so here's the leftovers. That was recap. The leftovers are, you can do the residuals and you can actually make a residual plot. So it's another scatter plot. And what you do is you, instead of plotting x, y, which is our regular scatter plot, we calculate the residual. We just saw that. That's why I reviewed it. Y minus y hat. Remember, y hat is the predicted value. And so here's what we graph. We graph x and we graph y minus y hat. And so, for example, up here, when we graphed 8, we would also graph -5. And when we graph 12, the other part of that ordered pair would be 11. And here we would graph 20 and -13. This, we're just graphing the x values together with the residual, which is y minus y hat. So let's see what it looks like when we plot a thing like that. And here's what one looks like. And you can see how they sort of cluster around 0. This is the typical way to do it. The x-axis will look exactly the same, and each of these x values is exactly where it should be. I think these are the chocolate Nobel Prize, yeah, chocolate Nobel data. And so they've plotted these like this, and this first one was just a little bit off the line, and these two were really, really close to the line, and this one was a little on the other side, and this one was way off, and so on like that. And what we are doing is, having plotted those, and it says, yeah, use technology. You don't want to ever do a residual plot by hand. You just don't. You could do a scatter plot by hand if you're out in the field and you just want a quick and dirty, let me see what the penguins look like on a scatter plot. And you've got 20 values, okay. But you don't want to be calculating all the R stuff and the Y hat stuff by hand and then subtracting all of those values, right? You have to calculate Y hat, then you have to subtract, and then do a scatter plot. Oh my gosh, way too much work. So we will never ever do one by hand. They don't even show us. I mean, it's obvious how you would do it, but no, we're not going to do it by hand. Once it's done, having used technology, the residual plot should not have any obvious pattern. It shouldn't even have a straight line pattern. If it has some straight line pattern, then that means there's some other pattern in the data. We don't want to see any obvious pattern at all, and we don't want it to become wider or thinner when viewed from left to right. And I think this chocolate one's a little hard to look at, but here are some examples at the bottom of the page. This is a great residual plot. And here's the x's, and there's the residual, and x with its residual, and x with its residual. And you say, do you see the pattern here? And your answer is, no, I don't see any pattern at all. Well, good, you're not supposed to see a pattern. We don't want to see any pattern. How about this one? Well, yeah, I see a pattern. It's going like this. Well, then what that tells us is that the regression equation is not a good model. And this was the thing a section ago when we said if you have a good model and you are within the scope of your data, that is, you're within the range of the lowest x and the highest x that you've actually measured, well, then go ahead and use y hat to predict. R has to be big, right? Your p-value has to be small for it to be a good model. If you don't have a good model, then the best prediction for the y value is y bar, right? The mean value of all the y's. And here, this is not a good model. Don't be caught using the straight line, a linear regression model if your residual plot looks like this. This is the one with an obvious pattern. The other way it can go wrong is if it gets thinner or fatter. And so here are some that are close to the line, close to the line, close to the line, kind of close to the line, farther, 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 farther. And you can see how it's spreading out. It mushrooms out. And if you see something like that, again, you do not have a good model. There is something else going on. If we had the scatter plot from the original data instead of this residual plot, we might be able to see something. The same thing here. You might notice, oh, hey, it's not a straight line. It's and there are other sorts of patterns that we will learn in 10.5. Not today, but soon. And that's kind of the idea, how you can use a residual plot as one more way to tell whether your model, your linear model, is any good at all.